In this video we will give you a brief conceptual introduction to stereo vision, stereo correspondence, and epipolar geometry. Before we start explaining the theory, let's take a look at a few practical examples of what we can do with stereo vision. One of the many use cases of stereo vision is 3D reconstruction of objects using images. Here is a 3D model of a flower that has been created based on 20+ images of the original flower. Here is another example of 3D reconstruction. Google has created a new 3D function which allows users to view parts of the world as 3D models. The top image shows a 2D representation of Oslo, while the bottom image shows the same area represented in 3D. When we talk about computer stereo vision, we mean the process of extracting 3D information from a set of related images. These images can, for example, be captured using one camera that moves around taking pictures from different viewpoints, like illustrated in the left figure. Another way is to have a set of two calibrated cameras that takes images simultaneously, as illustrated in the right figure. The main problem of stereo vision is to find where one point in one image is located in another image of the same context. For example, let's take a look at the left figure. We are interested in finding where the tip of the 3 in the right view is located in the left view. This problem is called the stereo correspondence problem. We can solve this by searching through the whole images pixel by pixel, but this is a really demanding task which is not viable. To simplify this task, we can use epipolar geometry, which is the geometry that describes the relations between the images. Here's an example of how we use epipolar geometry. We want to find out where this red spot in the left view, XL, is located in the right view. We can cast a ray going from the left camera through the red spot into 3D space. We then know that in 3D space, the red spot is located somewhere along that ray. By projecting this line onto the right view, using the fundamental or essential matrix, we get what is called an epipolar line, which is this red line on the figure. The fundamental and essential matrix describes the correspondence between the two images. By taking the coordinates of the XL point in the left view and multiplying it with the fundamental matrix, we get the epipolar line in the right view. Somewhere along this line in the right view, we should be able to find the same red spot that we also saw in the left view. It is a lot faster to search along the epipolar line to find the corresponding point instead of searching through the whole image. Here is an example of epipolar lines. By finding the corresponding points, we can calculate a variety of 3D information and, for example, achieve what we demonstrated in the beginning.